Hi, everyone. So I'm really excited for tonight's talk about XGBoost algorithm. I'll quickly introduce our speaker for tonight. Dr. Sophia Song is a data scientist and data engineer. She's been a data scientist in industry at CoStar, Accenture, and CoxAuto. And prior to that, she studied and researched machine learning in academia. So she's really versed on this subject, and we're so lucky to have her speaking for us today. She's actually given a talk for us before last year. I'll be putting the link to that video in the chat. But yeah, we're so lucky to have her back. Her lecture last year about decision trees and random forest algorithms was really well received. So I'm super excited to hear another machine learning lecture tonight. And with that, I'll hand it over to Dr. Sophia Song.
Okay, thank you, Jillian, and also thank you, Michi and Luisa, for providing this platform. Let us meet up and learn together. And let me share my screen. Yes, can you guys see my screen?
Yes.
Okay, perfect. And tonight, I would like to introduce XGBoost. Actually, after my previous talk at WWCode, last talk, like Jillian already introduced, I did a talk about random decision tree and random forest. Tonight, I would like to introduce XGBoost. It's actually, yeah, let me do the. So the XGBoost, actually, it's the single decision tree model, and Ensemble use a bagging algorithm to compose a random forest, and also use a boost algorithm to build up the XGBoost model. This three is a very important algorithm. So this tree tree-based family model is my favorite model, and so that's why I select this topic. So let's start tonight. The outline, I would like introduce some prerequisite, like the virus bias, ensemble method, grading boost, and XGBoost. The first three parts are all the fundamentals why we should use the grid, how to develop the XGBoost. So okay, let's start with the variance and the bias. So actually, we all know XGBoost is an ensemble model, right? The ensemble means combine different weak learner together, then to do a very strong prediction. So for most of the weak learner for the XGBoost, it's the decision tree. For the decision tree, I think it's a type. I'm pretty sure you may be aware that the decision tree is a type of flow chart which assists in the decision making process. So we can alternatively thinking that decision tree are a group of nested if-else conditions, so which can be modeled as a tree. In decision tree are made in the internal node. In the internal node, we make some decision for the for the output is obtained in the leaf node. So for example, for the terminal, like the terminal we call it is the leaf node. So then like the internal node, we make some decision, but the model output in the leaf node. So the decision tree, I would like to review some important term used in the decision tree, like the root node. The root node is the top level. This level we call it is the root node. So then we can have some internal node. The internal node, like I said, we make some decision in this level in the internal node. And also with splitting, the splitting point we based on some features threshold to do some splitting, then to split into different branches or to the different sub tree. So also the one important component is the leaf, sorry, the terminal to the bottom level. I'm so sorry. The bottom level node from there, we get the output from the model. So for the but for the decision tree, it's based on your purpose, your business purpose, or based on your data set. If your business purpose is pretty simple and also your data set is pretty small, so the data size. So in this situation, you maybe can build a small tree. A small tree, like I give here, I give a very simple example. In a scikit-learn, there is a data set is we call iris. We only based on the petal width, we can divide the different iris flower species. However, we also can base on your business purpose, on your data set, you can build up a very big tree, like the president election, right? So you can build up based on all the different factors, all the different features to build a very strong tree. So this is a flexibility in learning to provide the this decision tree has some advantages. For example, when you build up a decision tree, there are no assumptions as to some like the nature of the data or the relationship between the features. However, for other algorithms, these usually have some assumptions, like the linear regression model. We usually assume that the predict variable and the target variable, they should have a linear relationship, right? So however, for the decision tree, you do not have no assumption for the data or the relationship between features. So because there is no assumption requirement, so the decision tree can handle very complex data with some unknown or unspecified data relationship. So that's the advantage for the decision tree. However, because this assumption, but if we want to build up a very strong prediction, we need a pretty large, we need to a fairly large data set. Because there is no extrapolation of the data relationship. If the training data cannot cover the full range of the data and the relationship, then there will be some blind spots. For this blind spots, maybe can result in some large errors. So, however, in contrast, like other algorithm, like the linear regression model, so if they only use several points, they can build up a model and then can potentially yield a reasonable model that can make the prediction over a wide space. So yeah, so that's one limitation for the decision tree. So so another thing is, although we think the decision tree are considered as a very interpretable, right? However, if you build up a very complex model, it's still challenge to comprehend. Like the left hand, this model, this decision tree. So that's the decision tree's basic idea. So for the So here I would like to introduce the virus and the bias. So I would say this two concept is a very fundamental concept for the machine learning. So I heard from one professor, he introduced this two concept about if before you learn this two concept in the machine learning field, you kind of a child. After you totally understand these two concepts, you become an adult. it's from one professor. I think it makes sense because this very very fundamental. So for the variance and the bias, so I would say for the model, when you do the prediction, there is a residual. Can you see this small plot? Here is the prediction value and the real value. There is a distance, right? We usually call this one as a residual, or we also call it error. So, so for the machine learning, automated purpose is to reduce this residual, reduce this error. So optimize our model to reduce this error, right? So, but this error usually composed include two components. The first is the bias. The second is the variance. So here is the from one research paper. They explained this to demonstrate these two items very clearly. For example, this one this target is the real data. For all these black point, it's are the model data, model prediction. So all the distance between the target and the model prediction, sum of them together, some of them the distance square, the sum of the square distance, we got the model's error, right? So this error can compose this bias. The bias is for all, because if you have a very large data set, you can sample the two different data set. For each data set, you build up one model. So then from this big data set, you build up multiple models. For the multiple models, you have different prediction, right? You average all these models prediction, you got this centroid. This point is the average of all the models prediction. This average, the distance between this average to the target, this difference we call it is a bias. So otherwise, for the variance is all these black point, the distance from this black point, each model's prediction to the centroid, square all this difference, sum them together, then do the average, you can go to the variance. It means how different your different models prediction but all this data from one data source, right? The bias is means how your prediction different with the target value. So that's the two fundamental concept about the variance and the bias. So for one machine learning model, we usually have four scenarios, for example. But usually this error includes these two components, right? So these two components between the two components, there's a trade-off. So between the bias and the variance. But if your bias large, your variance may be small. So that's a balance. There is a trade-off. So with all this trade-off, there is four scenarios. The first scenario is it's the ideal scenario. Your model's bias is small, the variance also small. That's a very ideal scenario. The second scenario is your variance is small, however, your bias is very large, right? So another, it's very worse situation. The scenario is your bias very large, your bias is small, however, your variance is very large. So that's another, this another scenario. The worst situation, the worst scenario is your model, both the variance and the bias is very large. So this situation, it's a worst situation. So we usually, for the machine learning model, we want to reduce both the bias and the bias. So then to make the squared error is small. So I think make the squared error as small as possible. That's the purpose for the machine learning model. So here is I give you some mathematical expression for the bias and variance. When the bias is for like if for each model, if you have with your data set, you build up several models, right? For the model's output, you take the expectation value, then minus the target value. That's the bias. The variance is for each model, the simulation minus the expectation for all the models output, then do another to mean to take the average. That's the variance. So this is the variance. The mean square error. It's the you need to square the bias plus the variance. That's the mean square error to measure how well your model's performance. So this is the mean square error, right? So usually, because the mean square error includes these two components, there is a trade-off between the bias and the variance. But here is the plot to show in some range the bias is high in the first one. Here is show the model complexity relationship between the bias and the variance. So usually if your model is very simple, it's not capture the general pattern of your data, your model bias is pretty large. So however, because your model pretty simple, it's in the very low variance situation. So however, the final purpose, we want to find this red rectangle. We want to find it in this area. So the bias and the variance, both they in a very pretty low value. And yeah, so I think the final the purpose is to find in this area. We adjust our model to make our model located in this area, the bias and the variance. So that's the bias and variance concept. So yeah, so I think that's the variance and the bias. I hope it gives you a general idea how the machine learning model works. So the second part, I think, okay, yeah. So if no question about the variance and bias, next the fundamental method I would like to share is the ensemble method. So for the ensemble method, is because XGBoost is the boosting is a kind of ensemble method, right? For the ensemble method, there is there's two method, bagging and boosting, right? So these two. So usually, so if we with a very single model approach, if the build model is having high variance and high bias, like a previous session I introduced, we will usually with a single model, either we will maybe suffer the high bias, either we maybe suffer from high variance, right? So in order to conquer or in order to overcome this limitation, the people created this ensemble method, very smart people, and created this method. So so for the principle is for the ensemble is the idea of wisdom of the crowd. So it's collective prediction or many diverse models is better than any set of predictions made by a single model, right? So so here is like I said, so in the ensemble learning series, we call the weak learner the base model that can be used to build the blocks for design more complex model. So like here for this one, the weak learner suffered from high variance, because the high variance usually your model is very complicated. It's you capture some noise data. It's not only include the general pattern of your data, you also capture your data is too complicated. You capture some noise information. So then your model maybe simulate or predict the training data is pretty good. However, when you have new data in common, your model totally mess up. You cannot, because you in your model include some noise information, you cannot accurately to predict your test data. So in this situation, the high variance, you have the low degree of freedom models, right? So we combine weak learner to try to reduce this variance. So then, so your convert your weak learner to a strong learner. So the same thing like if your model suffered a high bias, so your model had a high freedom, high degree of freedom, but if you combine the weak learner, you can try to reduce the bias, so convert the weak learner to a strong learner. So that's the principle for the ensemble method. So for the ensemble method, we usually have two types or two categories ensemble method. So it's a homogeneous ensemble or heterogeneous ensemble. So heterogeneous ensemble, we usually stack like the weak learner, like the linear regression model, support vector machine, or the decision tree. We can stack all this model together to convert all this weak learner to become a strong learner. But however, today we will focus on the homogeneous ensemble, because this ensemble method include the bagging and boosting. These two methods, it's the decision tree based method. So today, so I will focus on, because today we focus on XGBoost. XGBoost is the boosting method, right? So it's a kind of a homogeneous ensemble. So on the following slides, we all the algorithm, the XGBoost, it's a combined the decision tree. All the weak learner are the decision tree. We do not use some heterogeneous ensemble. Only we use the homogeneous. The XGBoost combined the different learning tree. So for the bagging, so here is bagging and boosting. These two very popular, very famous ensemble method, right? So for the bagging is like the so we have a very large independent weak model, right? So we also have a data set, a large data set. For this data set, we do the random sample for so when we do the random sample, we usually use bootstrap aggregation, we call it. That's why it's the bagging. The bagging is the full name is bootstrap aggregation. So like here is the training data set. We have the training data set, right? So for the training data set, we have the sample. We do the subsample, and for each sub data set, we build up the one model. And then for all the subset, we build up the multiple models. Then do the so after we build up all the multiple models, if your problem is a regression problem, you can average all these models output. If your problem is a classification, you can use the majority vote to get the output. That's the bagging algorithm. So for the bagging algorithm, because each of the model, they are parallel. There is no relationship between all the data source from one data source, right? All the data is from one data source. However, the model is totally isolated. There is no relationship between these models. So it's a parallel model. So so for this model, we can because we usually use this model, the bagging algorithm, to reduce the variance. So yeah, that's the bagging algorithm. So for the boosting, the boosting is different with the bagging. The bagging, for example, you separate your data into different subsample data set. However, for the boosting, usually you do the, for example, you have the initial, have the first model. Based on the first model, you have some prediction, right? But for this prediction, you have some errors, right? You have some errors. Based on these errors, the next model, you will focus on or put much emphasize this errors and build up the second model. The second model also has some errors. So then, based on the second model error, you build up the third model. Then so then you can repeat all this cycle, and you build up the sequential models, multiple models. Then to do the final. Oh, I'm sorry, this is the typo. This is not the voting or average. This is the bag. My bad. Sorry. Sorry. Here is directed to the output. Here is no. I'm sorry for this one. I should remove. I think it's from the final model. The final model is already combined, right? Combined, learned from based on from the previous model. Then you can directly get the output. So, in short summary, the boosting algorithm is built up a sequential model. One by one, the next model always depend or rely on the previous model. Previous model's error, the next model always to put more effort or more to put more weight to predict the first model's error. So that's so second model learn from the first model, third model learn from second model. So that's the boosting. The boosting model, there is the relationship between one model to the previous model. It always has some relationship. It's not like the bagging. The bagging is the model is totally isolated. There's no interaction between the models. Yeah, so that's boosting. I would like to introduce the first boosting algorithm, AdaBoosting. So I'm very proud of this this algorithm. It's he is the author of this this algorithm. Is a professor from UCSD. His name is Yu Wu, and he is one of my professors when I pursue my master degree in UCSD. So he and with another author, they created this algorithm. This is the first boosting algorithm. So here I would like to introduce the algorithm, how it works. For example, I have all this data set, right? Based on this all data set, I would do the classification, red or blue. So I'm my first learner. So I build up then my first learner. But my first learner made 3 errors. These 2 blue label, it's wrong labeled. It will be labeled as red, right? This red label after my first learner, it will be labeled as blue. So these 3 points are error, the first learner. So for my second learner, I will increase all these 3 points weights, then build up the second learner here. So I build up my second learner. So all this second learner to correct labeled the previous error point, or these 2 points, this point. So this time the errors, previous model's error correctly labeled. This one is the same thing. However, for the second learner, I also still have some errors, right? These 2 points is wrong labeled. So, but based on this error, I will increase this weight. Then I build up my third learner. My third learner finally correctly labeled these two points. So this is a general idea how AdaBoost works. So finally, I combine or add all these learners together to build up my final strong learner. So the strong learner include all these 3 learners. So then the 3 learners all correctly labeled all the points. So that's the AdaBoost algorithm. So that's the ensemble method, bagging and boosting. Any questions? So if no question, I will continue to the gradient boost. So when we saw the gradient, we usually think there is a gradient descent. So for now here, I want to clarify this gradient descent is different with the gradient boost. The first for the machine learning model, we usually use the gradient descent to optimize our model, right? To make our model's loss function, the difference between the prediction and the real data. To make that the error is as small as possible. That's the gradient descent. So, so for the key takeaway from the gradient descent is, so the purpose is to minimize the loss function. So try to find the optimized parameter. For example, for this model, the parameter is M and B, right? So this parameter, we're trying to find this say M and B, these 2 parameter, the value to make this loss function, the prediction value, the difference between your prediction value and your real value, to make this loss function as small as possible. That's the purpose. So at first, this procedure, at first we initial all the parameter at the very initial position, like here for this one, you can initial at any point, but after the model learning, we can directly to adjust your model to make this your model loss function as small as possible. So, but however, so there is a hyperparameter when you do this process, the learning rate. For example, if your start point at this point, if your step is too large, you maybe can one step go to here. So next step go to here. So it's all this, your learning is wiggling through all this high position. You can it's you cannot never to stop by to the lowest position. In the lowest position, it means your model is optimized. It's an optimized model. You have the lowest error, this loss value, right? So, however, if your step is too large, it's wiggling in this area, you cannot get to the optimized parameter. So, however, if you use a very small step, for example, if you start here, use a very baby steps, very small, it will take you a long time to get the optimized point, this point, right? So that's the learning rate. You need to select a very proper learning rate to, so each time your learning should go how large, so how fast you can find your optimized hyperparameter, this M and B. So that's the goal. So the gradient descent is an algorithm to find this set of parameters that optimize the loss function, this gradient descent. So however, for the gradient boost, so for the gradient descent, we use to take the model parameter, right, to find the optimized model. So like the model's parameter, like I said here, the B, this M and B. However, for the gradient boost, it's you take your output, your model's output, then to do the to optimize your model. So for example, here you have an initial for your model, you have initial guess or something. When you build a next model, your difference between your prediction value and the target value, it's when closer. When you build another model, you is more closer. So when you, so it's step by step. Your models, the loss function, the loss function becomes smaller, and so that's the general idea. So that's the gradient boost, how it works. So here is I want to introduce a regularization, because XGBoost use a very because in order to avoid the overfitting, XGBoost introduced a regularization item. So what's why we use regularization? Because for example, if we have data set, right, we have data set in this pattern. If we use a very simple linear regression model, we will have a large bias, our model, right? However, in order to make the loss function as small as possible, we increase our model's complexity. So our model can capture each data point pattern. However, each data point may be not a general pattern of the data, right? So it may be because this point is in this location, it's maybe caused by some noise information, right? So if you adjust your model to make it a very complicated, it's your model easily to overfit. What I mean is overfit. The data set here is the model is very good to predict your training data. Because in your training data, you saw all your data pattern, you capture all the patterns. So then, however, when you have new data coming, right, it's very it's not accurate to do the prediction for the new data, because in the training data you sum this pattern or this item, you add it into the model. Your model structure is maybe emphasize some noise information. It's not a general pattern. So here this one is the optimal model. So it's a general pattern. This model is the bias is pretty small. Your variance is also not so large, right? So that's the overfitting. In order to avoid overfitting in the machine learning, we introduce this regularization item. So here, like, so before we only focus on the loss function, only focus on the difference between your prediction value and the real value. However, we added this item, the lambda and some order, the bit, the variable square. So this beta means it's your model parameter. So because this loss function is always positive, right? So if you still want this item as small as possible. However, because the beta, this square is also a positive value. So in this situation, you want to make this whole item as small as possible. You have to reduce your parameters value. So it means you reduce your parameter weight, or even sometimes you dismiss the sum of the parameters. It means it's maybe some parameters value reduce, or some parameter maybe become 0. So that's the philosophy how to do the regularization. So then you make your model not maybe only finally only have these 3 items, but all the other items maybe already panelized or remote because it is this item. So that's the regularization. So also based on all the previous video, I think we can get some ideas. So for the for the machine learning model, we usually have the objective model, right? The objective model usually have include the 2 parts, the training loss and the regularization term. These two items. So we finally go to build up this objective model. So the training loss is actually it's nothing but the difference between the actual value and the predicted value. So it's usually to measure how well your model performance. The regularization is measure the complexity of your model. It's to avoid or prevent your model too complicated and to avoid the overfitting. So that's the machine learning models general the final goal to get this object model. Here, so I will give you an example for the AdaBoost how actually AdaBoost it follows the general machine learning rule, also follows the AdaBoost rule, right? So AdaBoost, AdaBoost, how it works here? Here I have a data set, right? Heart disease. So for the heart disease, here is the label. I want to so here is the prediction we usually to predict for each person if I have 1 record. For this person, based on these 3 features, I want to predict the probability this person to get the heart disease. That's the goal. That's the final prediction. It's the probability get the heart disease, right? So usually in the reality, so our model like this model, so the range, this model's output, the range usually from the negative infinity to the positive infinity, right? So however, the probability range is from negative, 0 to 1, right? So here is the logic function to map this probability to the real world, to map the probability from 0 to 1 to the negative infinity to the positive infinity. I think that's a legit function. So it links the probability to the real world, negative infinity to the positive infinity. However, because in this situation we want to predict the probability, right? So we do not want this the range should be from 0 to 1. So we need to inverse this function to get the probability. The log, this is the log odds, right? This is the odds. So then we can to exponential the both side. So then to do the finally we can get to the probability. This actually is a logistic regression model. So so here, so for the AdaBoost, we should have, so I think for the AdaBoost the same, we should have the initial guess. So for example, based on the historical data, we have the initial guess. How we get the initial guess? We use this logistic regression model and use the log odds to get the probability for each person. If we have a new person coming, we can based on the historical data to use this log odds to get the probability. When you coming, a new person come, we can tell them, oh, there you maybe have the 70% to get the heart disease. That's the initial guess. So for any person new coming, we can give the initial guess to guess there is 70%, you maybe can get heart disease. That's the initial guess. So based on this initial guess, we can get the residue. So actually the gradient boost, their prediction is this residue. The residue is the actual value minus the predict value. So that's the gradient boosted prediction. It's a residue. So the residue is means your real probability and your models output probability. We get the residue because our initial guess is 0.7. So because for the first person there's no heart disease, right? The probability is 0. We can get the residual is negative 0.7. So the same methodology for all other records, we can got all the residual for each record. So then we can build up the first model. The initial is we just use the logistic regression to get to the first initial guess. However, for here, we will build up our model based on some feature here. The feature, we have 3 features, right? So based on this feature, the blood circulation, we can build up the first model. For each model, we get the leaf, or we can list all the residual in this leaf. Then we can base. So how we get the output? We cannot directly use all this residual, right? This residual from the previous initial guess. How we can get the residual smaller? So here we introduce this one. We use the residual sum together for each leaf node. We sum all them together, then divided by the previous probability 0.7 times 1 minus 0.7. So that's this for each leaf. You can use this function, get the output. So then based on this one, we can get the output 1.43. So for this leaf, we got this one. So all based on this equation, we got all the output. So however, like I said, so for all this output, if we directly plus this one to the previous model, so it's your step is too large. So we usually to use a learning rate to reduce your model's impact for the whole model. So for example, for this one, our output is 1.43, right? If one person, one record based on tree, we end up in this and leaf node. So in that situation, we use our initial guess plus the learning rate time this output. We got this value, but this value is odds. It's not a probability based on this logistic regression, but take the odd. So then we got this person's get the heart disease. The probability is 0.73. So for this person. And so actually for this person, the first guess is 0.7, right? 0.7% However, for this one, like this one, our percent the probability is 0.73. Actually, their actual value is 1, right? So now the new prediction is more closer compared to 0.7. So if we use one new model, our model's prediction is a little bit closer to the real data. That's how the gradient boost. So if we build up the second model, our second model to push our model prediction more closer to the real data. Yeah, so that's how this gradient boost works for this one. This one is the classification issue. Actually, it's a probability. We sometimes we set up a threshold, like your probability about 0.5, we classify as one label. If it's smaller than 0.5 probability, we class to another label. So this kind of a classification the XGBoost. Actually, this XGBoost, that's also how XGBoost works. So for the XGBoost, it's all based on the previous knowledge, right? We have the initial guess, then calculate the error based on the previous model, then to build up a new model to predict these errors, then add this previous model to the ensemble, then to got a new so like I'm sorry, here, this one. So always add all this in the differential to your previous model. Add this differential to your previous model. Finally, your final model will be very close to the target. I think that's the XGBoost how it works. So yeah, so it's the same thing. I plot another plot. It's the initial guess plus the learning rate times your first learner's output, then plus the learning rate times your second learner's output. Then you go to the final prediction. So it's the same thing. For the XGBoost, XGBoost, they use the same methodology. So we all know XGBoost is belongs to the machine learning, right? For the XGBoost, we also should have these two items, like the training loss and the regularization, these two items. So for the XGBoost. So here, I want to one item by one item to solve it with the mathematical, for the regularization term for the XGBoost. Here is the function for this one. So so actually the regularization term is to measure your model's complexity, right? So for the XGBoost, it's the same thing. The complexity will include two items. It's T and this WG. The T is the number of leaves, how many leaves in your model. If you have more leaves, it means your model more complicated, right? So for the weight, this weight, if your weight is large, it means this model, you have a large impact for the whole model. So these two items to measure your model's complexity. So here the gamma and so these two, gamma and lambda, so this two is actually a hyperparameter. It's you predefined. When you build out the model, you need to predefine this parameter. It's not the model, so it's a hyperparameter. So we do not need to worry about that. But sometimes even you do not set up these two parameters, the model have the default parameter. These two default values. If you do, usually this value, the gamma, usually I think 133 or something. I forgot exactly. This lambda is around 0.1. Yeah, so something like that. So usually we use this. If for example, I have this model, right? I have 3 leaves. I use this gamma. This gamma is already predefined. We time this 3. I totally have 3. These 3 leaf node, and then plus all this weight. This weight, like this here, the weight is you the learning rate times you this leaves residual, then divided by the how many records inside in this leaf. For example, this residual plus residual plus together, then divided by 3 is this leaves weight. So for each leaf, you have a weight, right? So sum of them together, then you got then plus your gamma times your total leaves, number of leaves, then you got to the regularization term. So that's the XGBoost regularization term. So then we will focus on the loss function, the loss term. So for the loss term, so here because like XGBoost is the additive boosting, right? We have 2 models. We just this is a simple diagram, just simplify the diagram, just plus it together. But sometimes we need to in the reality, maybe add some weight or add some other factors. But here, so for the loss function, so here is a loss function with this loss function. This is a loss function part. So if we optimize this loss function, it's not only hard. It actually is sometimes it's very hard. It's impossible. So in order to sometimes in order to solve this issue, if you very hard to describe some relationship, you can use some approximation. So here we so for the XGBoost, we introduce the Tyler approximation. The Tyler approximation. I maybe do not want to spend some time on this item. You can to go back to do some research about this one. So usually you can use this this function, original function, time plus the first order first order derivative this function, then the second order or derivative. So then plus all this together to approximate your object function. So all this here is the loss function. So here the main idea, we maybe sacrifice a little bit accuracy. However, we simplify our model. So that's the general idea. So you in generally, if you add this to, actually you can add to the third order, fourth order. You can add all this one. The more items you add here, the more accurate. However, if you add more items, your time complexity will be high. So in order to simplify, you use second order is already good enough to approximate your loss function. So here we use so use the Tyler approximation to optimize this loss function. So for the objective, so here we use the loss function plus the first order I'm sorry. So first order this model, so the current model. So the second order derivative, your current model, then plus the regularization. So here the first order is usually to do the partial derivative for your model, the loss function. Here is the loss function. The second order, the partial derivative, your loss functions. So here, actually, if you see, this is pretty complicated. However, but finally, when you do all this math, it's very beautiful. It's very simple, actually. So for example, for the loss function, for the regression, we usually use this loss function, right? For the classification, we usually use this as a loss function. This loss function, like the cross entropy, you can go to the largest regression model or something, you can get this loss function. So for the classification and the regression loss function, we can bring all this loss function into your loss function. We just approximated, use the Tyler approximation. We use the initial guess, the first model. Actually, this G1 is the first order partial derivative, your loss function. It's the second order, the partial derivative, your loss function. So all this we plus together. This 1, 2, n is the records. How many records you have in your model? So then finally, because all this L, the first order for the first item, the L1, Y1, P1, 0, these are all the constant, right? So when we calculate the derivative, the constant, we usually is 0. We totally can ignore them. So we only concern this the first order partial derivative, second order. So we plus all this together, we can get this function. So finally, our loss function become this function, this one. So when we do the loss function, then we can get the optimize. If your derivative is equal to 0, so in a 0 point, we can solve this function, right? So here, so when we so here we put it a 0, we can solve this the output. Our prediction output x prediction is equal to sum all the first the first order partial derivative together, divided by the second order partial derivative. Then you get your output. Actually, when you know your loss function, based on this loss function, you can know the first partial derivative actually is a negative, your residual. For the second order of your partial derivative is equal 1. So it means it's the denominator is the negative, then the sum, if we ignore this, so the sum of your residual divided by, if your model is the regression model, divided by the sum of your records in that leaf node. So it means it's very beautiful. I mean, so final output is your sum of your residual, then divided by your number of records actually, then plus your this regularization parameter. So for the for the classification, if we can use the same thing, finally we get the output. The model output is a sum of residual, then divided by the probability previous models probability time 1 minus previous models probability. So this is how we get the output, how we get the models simulation. So for example, here it's consistent with this one, with here. With here, how we calculate this? How we calculate this one? We use this classification, right? We use this sum residual, then divided by the previous probability. So I introduce this function here, and here we prove why we use that one, because we introduce we approximate our loss function with a Tyler approximation. So finally we got to the regression output. We can use this formula to calculate the classification. We can use this formula to do the calculation. So then for the current model, we can use the previous model plus the learning rate, then time the output here. So actually we can use the learning rate time this function. So the residual sum of residual. So then to divide your number residual, then plus the this item, the lambda item. So this is the general idea how the XGBoost works. So however, this is only the algorithm how the XGBoost works. So for the XGBoost, they had a very powerful. It's a very powerful algorithm. Right there, it's for example, XGBoost is a sparse aware algorithm. So for example, here I have one record. I have the miss value for the month, right? So actually. So for this one, it's the XGBoost can set up a default so for example, if the XGBoost can based on the similarity score to calculate, for example, I can for this this record has a missing value, right? But for this 3 record, I do not have any missing value. So based on these 3 records, I set up for each of I sort this month, and based on this first 2 value, I set a threshold. I use this average 2 and 4 average as 3. I use this one as a threshold to build up a tree. And the first time I use this threshold, I put my missing value, this residual, into the left node. The second time I put this 6 into the right node. For the second thread, so 4 to 6, I also build up a tree and put this 6 to the left node and to the right node. So based on this equation, to calculate the similarity score. So for all these 4 trees, I calculate similarity score, use the highest similarity score. For example, if this tree, the similarity score is the highest, I use the month equal 5, large or equal 5, this tree as the default value. So if in the new incoming record have the month missing value, I will put that record into this node. So that's how the XGBoost deal with the missing value. It's a sparsity. It's a sparsity actually. Sometimes you have missing value. Sometimes it's a zero value. Or the record, all your feature, all the feature value is zero. So it's sparsity here. The sparsity means the missing value. So this XGBoost sparse awareness. So another thing is XGBoost is a great
Dr. Sophia?
Yes.
Sorry, we had a question in chat, and it was relevant to the slide. So,
okay.
Jessica was wondering, is month a target label?
Which one?
Month.
Oh, month. Here, this one.
Yeah, on that slide.
Yeah, so this one, right? So
yeah.
This month. What's the question? I'm sorry.
Is month the target label? And Jessica, feel free to unmute if.
Oh, no. The target value is the weight. I'm sorry. The weight. The target value is weight for the baby. It's the baby weight at the 2 months, 4 months, 6 months, right? So the first, I use the first initial guess. So use this one and use this 3. Actually, this 4 as average as the initial guess. Then do the residual between your initial guess and your real data. So then get to the residual. The residual, the target value is weight. The month is just a feature. I'm sorry.
Sorry. So month is a feature engineering technique.
Correct.
That's what you are doing. Okay.
Correct. So your feature, if your feature, so usually this is the target value, right? So if your feature has some missing value, how you deal with this one? So for the XGBoost. So XGBoost is based on the similarity score to set up a default value. So then in the future, if you have new missing for the month, if you have the new record, the month still missing, we use that default value to fill that missing value.
Okay, sorry, I have more questions. XGBoost is a library. XGBoost is a library. And this, everything has been handled behind the scene, right?
Mm-hmm.
And how do we know, or how we would encounter this concept that you are showing us right here?
So actually, I always have I always thinking. So I don't know if I understand your question correct or not. So you said why we need to understand all this behind algorithm.
No. I learned this before. I just XGBoost is a library, as I know.
A library,
so,
correct.
Right.
Yeah.
So we always just calling the library, and we're setting or tuning hyperparameter. That's all we do. Yes. And you are giving more detail of the explanation on whatever.
Yes.
Behind the scene. I was just curious, how are we gonna encounter this if we are doing data scientist, data engineering work? How that help us?
So actually, it's a very good question. So sometimes currently, the many algorithms, they already packaged together, build up a library. Then you can directly import their library, directly use it. However, I always have, in my mind, I always want to understand the behind the scene. You understand each step. Then when you do the hyperparameter tune, you still have some idea. So in which direction I needed to tune this hyperparameter. So for example, if you tune the hyperparameter, right, your model's difference, your model prediction and your real data, their difference to change to a specific direction, right? So in that situation, you know how to tune your model to make the difference to a correct direction. So even if you do not understand, sometimes you tune your hyperparameter. It's maybe the model go to the wrong direction. Maybe if you do not understand, sometimes you maybe don't understand, don't know still. So I know, but sometimes for me, I always a person want to know and hold how it works. So then it's give you a deeply idea to do the mod. See, actually, the XGBoost and random forest is already matured algorithm, right? So this algorithm, they already developed well. However, if you want to, like the XGBoost, Granny Boost, then before the AdaBoost, it's a developed history. It's a developed in different stage of development. If in the future you understand the value deal, in the future maybe you can build up your own boost algorithm.
I see. Of course, when we are tuning or ensembling the model, this is very important to know which direction you are heading to. So if you can tell us more while you are continuing on the class, I will greatly appreciate it.
Okay.
Thank you.
I will have a demo. It's very Thank you. I think it's a very good point. Yeah. So actually this active here is another thing because XGBoost is a great algorithm, right? So like here we try to use each threshold to do the splitting, trying to figure out which is the optimized model. However, if you have a very big model, big data, it's very time consuming. It's very so it's not easy to handle that. So based on that, they use the percentile. So for example, you can quantile or something to do the splitting. So actually there is another concept is called the I believe it's called a weighted sketch, quantile sketch. That's concept here. Yeah. So they weighted each data point, then to combine this and build this weighted data point to form this histogram. Use this histogram to create the percentile, then to do the splitting. That will save much time, right? So this another advantage of the XGBoost. Another thing is XGBoost also a cache awareness access. So for example, because for the XGBoost we calculate a lot of the first order partial derivative and the second order partial derivative, right? So if each time you build a new model, you calculate this one, it will be very time consuming. But for the XGBoost, they store all this the partial derivative into a cache, into your cache. Then if you use it next time, you can direct it from the cache to read it rather than from the hardware or some hard devices. So it also save a lot of time. So another thing is the XGBoost also if your data set is very large, if you your data in a database, so the XGBoost use the shader technique to split your data into a small piece and store into a different hard device. So another thing is also the XGBoost to compress your data store your data into the cache. Then when you use the data, just take some time to uncompose your data and direct to use it. So that's the that's XGBoost. I think I already finished my lecture, and I can give a demo. So here is a demo. Yes. So it's too small for this. Can you guys see the clear? I can.
For me, I still see the PowerPoint.
You still see the PowerPoint? Oh. So now you cannot see my notebook? No?
No.
Oh.
It looked like you started to move the screen and then maybe Zoom got frozen. I've seen that happen before.
Okay,
So
let me stop sharing and resharing. Okay.
sorry about that.
Thank you. Yeah, I think. How about now? Can you see my screen now?
Yeah.
Okay. Okay. So it's I mean, it's the size is too small. Can you see it clear, or it's too? View. Oh, yeah, I can't. Yeah.
Oh, that's great. Thank you.
Okay. Yeah. So I would use the XGBoost to compare to the decision tree and the random forest to see how these three models performance for the same data set. Yeah. So for the classification, here I only use so first I want to see the XGBoost, like a moment ago. I think that lady she mentioned. They already have the library, right? So we directly to import it into our Python notebook or into the Visual Studio or PyCharm. You can directly use it, right? Yeah, so yeah, so tonight my lecture more focused on the behind the scenes mechanism. So here I want to demo so we can directly import the XGBoost. The XGBoost we have two different models, classification and regression. So usually for other algorithm like the decision tree and random forest, they already included in the scikit-learn. However, the XGBoost still it's a separate library, not in a scikit-learn yet. So for the XGBoost, I import from after I install the XGBoost, I import the classification and regression, and then I use a very toy data from the scikit-learn the address data set to load this data set, then to do the decision tree to do the classification. First I split my data into the training, test, and then these two data sets for either the predictor variable and the target variable. So after I use this decision tree to do the classification, so then this is the model performance for the decision tree. So the training data, the accuracy is 0.95, but test data is 0.96. So the pretty good for the decision tree. For the random forest, we can see the training data and the test data both is better, little bit better than the decision tree. But for the XGBoost, we can see it's also better than the random forest. So here I summarize all these three models' performance. Because it's a toy data, it's not so large, so the model performance is pretty close. However, we still can see the XGBoost, the performance is it's best. So yeah, that's why XGBoost is become most of people is a popular algorithm in a Kaggle competition or in other so application. So even the XGBoost is compared. It can sometimes it may be better than the neural network, but sometimes it's equal. At least sometimes it's equal to the neural networks model performance. So about the classification, here I have the regression demo. For the regression, I also so here I download some data from the Kaggle for the house price prediction. So totally for this data set, we have the 81 features. And also for these features, after I load my data into my notebook, I think I want to know the data type. Some data type is maybe the numeric data, some is maybe categorical data, some maybe the textual data, right? So I want to know the category, the data type. So here I found there is totally 38 numeric feature, and so for other feature, there is 43 is a categorical data feature. So I totally have 81. I think it's 81, right? Sorry. Yeah, I totally have 81. So some data is numerical, some data is categorical. So for the data, we needed to understand their data type. So then So next step is, because the data quality, you need to know how the missing data. So I know for the XGBoost, it's awareness, sparsity awareness. However, if your data is too much missing, for example, for this one, it's 93% missing. Also for someone, it's 99% missing. For this kind of data, I do not think it's useful. So for the missing data percentage, give us some ideas of how the data, the missing data issue. We can remove if too much data is missing, we can remove them. So another analysis before, we needed to understand the correlation between the features and between the feature and the target variables, right? So for here, the price is the target variable, right? The sale price. So we can see, so for example, so the year built, this one, this column, the year built, it's very, I think at the very, I think this, the overall condition, we can see this overall condition, this one, ID, this one, this summer's class, yeah. Let me see. So we, based on this color, we can see that each between between variables, their correlation relationship. We understand this relationship between the these different features. We also, the XGBoost can based on this one, we can their correlation, based on this correlation score, we can sort to yes, to sort, yeah, to understand the sale price, which one is the most important feature to affect our sale price, right? We understand to different variables have the different relationship between this variable and the target variable. So here I did some data outlier detection, and also I did some missing value fitting for even some feature. If you have too much value missing, we maybe, I think it's better to do the missing value gap fitting. For the, I think like the XGBoost random forest, the some missing value is not, sometimes it's not so important, but sometimes if you have the you fail gap fitting, I think it's also to get a better model performance. So this one is I also did some some feature engineering. For example, if you if I have binary category, like the has pool or no pool, has a second floor, no second floor, for example, I need to enable to label them, to encoding them, to do a binary encoding for this kind of variable. Sometimes if you have multiple labels, you need to do I have encoding, label encoding, I do for that kind of variable. So you have binary labeling and the multiple label encoding. So all this data engineering, feature engineering part. So I'll finish that. So actually the data processing and feature engineering is usually is very time consuming. So like the model, if you import that model, then to direct it to do the prediction. For example, for the decision tree, I do the regression to based on the train data, and then do the then to predict the test data, right? So I train the model, use the train data and the test to the prediction for the test data. So this is the model performance. For the random forest, I also build up this model and get this model performance. So XGBoost finally is the same thing. I did all this one, and I summarize all this model performance. We can see that. So for even for this pretty complicated data, so for the regression, the XGBoost performance is still outstanding here. So compared to the random forest decision tree. So yeah, so that's the model demo for this one. Yeah, I think that's all I have tonight. I'm wondering, do you guys have any questions?
Thanks for the demo and the lecture, Dr. Sophia. We
You're
had a
welcome.
couple questions in chat about if the Jupyter
Sure.
notebook or the code will be shared.
So that okay. So which part was it? What's the question? I'm sorry. Oh, here is the chat.
Oh, they were wondering if the demo code will be shared anywhere.
Oh, you share? Yeah, I think that's yeah, I can share. Yeah, so I can send it to you. Maybe you can share. Then, so how about that?
Okay, yeah, that sounds great.
Sure,
We can do that.
Okay.
Yeah, we can stick it in a Google Drive and then post the link to the drive on the meetup post.
Sure.
So just
Yeah.
keep an eye on the meetup post.
Okay.
Are there any other questions for Dr. Song? Feel free to unmute or write in chat. Oh, it looks like Paul has a question. Paul, would you like to unmute to ask your question, or would you like me to read it? I'll go ahead and read it then. Trying. Let's see.
Can you hear me now?
Yes.
Yeah.
Hey, thank you. Sorry. Yeah. So hey, Sophia. So first of all, great presentation. Thank you for the detailed presentation. I was just wondering. It seems like everyone, pretty much proves that boosting is better than bagging for some reason.
Yeah.
And obviously every use case, every project needs to go through model selection, and there are all kinds of reasons why somebody might throw in a bunch of estimators in a pipeline and then select the best one that wins for all kinds of business or data related reasons. But I was just wondering if as somebody who is hands-on producing models as a pretty much as a occupation, do you ever see bagging actually being useful or winning against boosting? And if yes, are there certain heuristic rules, certain scenarios where that happens, or does it always pretty much come down to bagging beating boosting?
Hi, Paul. I think it's a very, very good question. So actually, both bagging and boosting are very good algorithm. However, from the complexity, I think XGBoost is maybe a little bit complicated. It's not easy as the random forest to handle sometimes. But if for the if you think XGBoost its attribute is you very easily handle. You can use a very famous, how to say, you can use, I think XGBoost is always my first choice. But like I said, XGBoost also has some limitation. And no, random forest. I mean, random forest, because the model to model, they are the parallel, no interaction between the model to model. And sometimes if you, because the model, maybe they are correlated together, maybe their error is very same. For example, if you totally have 3 model, right, decision tree, however, these 3 decision tree for the random forest, these 3 decision tree have the similar error. So in that situation, your random forest does not work well. Do you know what I mean? You cannot well to reduce the variance. But for the XGBoost in this situation, the XGBoost, because each model is learned from the previous model, right? In that situation, I think the XGBoost is much better. Another thing is the XGBoost the random forest has its own advantage because each model is parallel. parallel, right? You can distribute all this random forest tree into different, distributed in the different server, right? You can the parallel to compute, to do the model training. It's much faster sometimes. So that's what I'm thinking.
Sorry, on the last point, yeah, the random forest is faster or XGBoost is faster?
Random forest is it's much, if you have very large data set, right? You build the random forest, you build up the model is parallel, right? You can distribute all this model into different server, then finally collect all this data, all the output into one server or some to do the processing. The random forest is much faster if you have distributed server or system.
That was actually going to be my next question, but I see that somebody posted something, so I'll let you get to that one. Maybe I'll add something in the chat.
Okay.
Thank you.
Okay. Yeah. Thank you, Paul. Thank you. Yeah.
Thanks, Paul. That was really considerate of you. So a Zoom user has a question. If you'd like to unmute, go ahead. Otherwise, I can read it for you.
You can go ahead and ask.
Okay, thanks. So their question is, how does this compare to deep learning algorithms like, and I'm probably going to pronounce this incorrectly, LSTMS or 1D-CNNS performance-wise? And when do you know which to use?
So actually, the LST, so that one, I think it's you already use the language processing, right? The sequential data set to use that long-term short LSTM, right? So that one is usually use the language processing, some sequential data set. If you have that kind of data, we usually use that kind of data. So for the neural network, I would see it's if you have the image or language that kind of unstructured data, you can use that neural network. It's definitely it's your first choice. But like I said, XGBoost compares the neural network, the complexity. It's still, I mean, the XGBoost is still not so complicated like the neural network. So another thing, the neural network is totally black. It's a black box. You cannot control something, right? You cannot control sometimes. You only can tune the hyperparameter sometimes, but you cannot control so much things, so many things. Another thing is, for example, XGBoost, random forest, and decision tree. There is a very important feature is you can rank your feature importance when you do the prediction. You know which feature is the most important feature, which one is the most important to affect your final prediction. So in that situation, you can select your features. Even if you have too many features, you can do this feature selection, then to ignore some important feature. I think that's a very important part for me. When I do the model prediction or something, I need to rank the importance or the different feature. So then I understand which feature is very important or how important. So they can give you a score how important or this for this feature or something like that. Yeah, I don't know if I answer your question or not.
That was so. Thank you.
Okay, thank you. Paul, go ahead.
I did it again. All right. Yeah. So you were already kind of going down that path of when you were talking about the differences between random forest and XGBoost. I was just wondering if you use XGBoost in production, or maybe some of your team members implement that in production. I was wondering if you have any lessons learned, any scars, or any cool stories to share about things maybe going right or going very wrong with XGBoost. Is it easy or more difficult to maybe reproduce things when models break in production? Feel free to share.
Yeah, I think it's a very good point. We indeed some error happened after we deploy the model. It's but it's not from model, it's from a data. Sometimes your new data, we have new data coming, right? So however, like I did this data processing, all this stuff. So it's the data type. So the new data, I don't know why it's the same feature, same column feature, but this type it's changed. So in that situation, so some error happened, but not the model issue. So yeah, so I have that issue one time, but for the model, I think after deployed, didn't match the model issue yet. But the data causes some issue sometimes. Yeah. Hi, Paul. Yeah. So I think.
Yeah, no worries. I know you're not a ML engineer, so I completely understand.
Yeah.
If I was just curious.
Yeah. So, but because currently we use the AWS to deploy the model, AWS they already have this each state deploy. It's very easily to the CityMaker Studio. It's very easy to deploy. They already incorporate all the pipeline together and very easily to deploy them. Yeah. Okay. But anyway, thank you, Paul. I think it's a good point. If in the future you have some issue, I hope you can share. Yeah.
Absolutely.
Yeah. Thank you.
Thanks for the questions, everyone. Are there any other questions? Feel free to unmute and ask, or use the raise hand feature, or write it in chat. Spencer says, thank you, Dr. Song.
Thank you. Thank you all. Yeah. Have a good night.
Cool. Well,
Bye.
we can wrap things up then. So I'll pause the recording.